The future cannot be predicted, but futures can be invented. It was man's ability to invent which has made human society what it is. The mental processes of invention are still mysterious. They are rational, but not logical.
The Interplanetary Podcast. The exploration of space for the benefit of all humankind. Your hosts from Estec Open Day, London and Nordwijk, Julio Aprea and Matthew Russell.
Oh yeah, baby. Gabor.
Dennis Gabor.
Dennis Gabor.
Who was
Tell us
Dennis
a bit
Gabor,
about,
Matt?
Me tell you a bit about Dennis Gabor. I think he was a Hungarian British electrical engineer, Nobel Prize winner in the year of my birth, 1971. There
And
we go.
he won the Nobel Prize because he was inventor of holographics.
Wow.
Correct? So, but most important, why did we choose that quote today? And
I
why
don't
are we
know.
live?
We are live, are we?
Because we are here today live at the ESA Open Day of 2021 entitled
Inventing the
the Future. Correct.
Yeah.
And talking
he
about
wrote
the
a book.
future, look at where I am.
wrote- You are in the future. You're set in the future.
I'm
Yes.
here in the Hertz Room, and I'm sitting together next to Peter de Maagt, who is the manager. He's the head of antenna and sub-millimeter wave
Correct.
here at ESA, and he's also a very serious underwater photographer. And he's here. He will tell us what is this place. Does it look? How does it look from your side?
It looks absolutely awesome. I did see it in real life a few years ago, and it's still one of my. I think it is my favourite room at Estec. But I've got, obviously, being an acoustician by trade, there's something really special about that kind of room. But I have to say, I didn't realise until last night that it's got the best acronym ever. I just thought it was named after Hertz, the great physicist, but it's not, is it?
It's an acronym.
No,
Welcome, Peter.
It's an acronym.
Yeah.
It's an acronym. Welcome.
Welcome, Peter.
Matt. Welcome, Julio. So it's a pleasure to be here. No, it is indeed an acronym, but of course it's playing with the words, and Hertz being a unit in which we indicate the frequency of electromagnetic waves, it really made sense to select that acronym.
Yeah, it really does. So what is the acronym?
So you can read it.
I'm going to throw you under the bus there.
I have all the show notes and all the cheat sheet here. It's the Hybrid European Radio Frequency and Antenna Test Zone.
I was just checking him.
Yeah, I know you knew it.
Although there seems to be an A snuck in there. It should
Who
be
came up with it?
Hertz.
Actually, that's an interesting question because we had a contest asking people to submit ideas how we were going to name this chamber. In the past, it was called the Compact Payload Test Range, and everybody was confused because of the mere size of this chamber. And then we said, okay, we're going to enter the Compact Payload Test Range, so they were expecting some sort of a shoebox-sized facility. But it's huge. So we added another piece of equipment, and then we said, okay, we have to change the name. So we had a contest, and we had contributions from worldwide, from Australia, from Argentina, from New Zealand, Australia, from Europe, from all the member states. And in the end, we decided that Hertz was the winner.
I've rarely seen an acronym that good, that works so well.
Yep.
I mean, it couldn't be better, could it? Yep. So obviously, I'm looking at it, and I'm seeing loads of blue triangles instead of beige triangles.
Yeah.
What is the difference between that anechoic chamber and an acoustic anechoic chamber that I was used to?
Yeah, well, actually, there are more similarities than differences, I have to say. The biggest difference is that our room is made to ensure that we don't have reflections from radio waves, while your room is made to prevent reflections for audio. In here, if you have audio, if you would record here, there would be still some reflections. So in a recording studio, you prevent audio reflections. But here, we just made sure we need to test the antennas, that there is no radio wave whatsoever reflecting. We're mimicking space, if you want. So in space, also, we don't have any reflections. We're inside a room, and we have to make sure that we mimic space as good as we can.
And here we test mostly the antennas subsystems of the spacecraft,
It's actually in here because this room is so big. We test the antennas on the spacecraft, on the
full
satellites.
spacecraft.
On the satellites, yeah.
I assume some pretty famous spacecraft were tested here.
Yes, that's a nice question. Famous, what is famous? I have to be careful here because we have plenty of customers. We measure for all directorates within the agency. So we measure spacecraft for navigation, for Earth observation, for science, for telecom, even antennas for launchers. So if you have been working for 5 to 10 years on a certain satellite, I'm pretty sure that particular satellite is the most famous satellite for that particular person. Just a few recent ones. We have been working on JUICE, the spacecraft going to the moons of Jupiter, Earth observation satellite, METOP, MTG, name it, Galileo, of course, the navigation satellites. So we had our fair share of measurements here.
Excellent.
Yeah, I love the fact that you're doing JUICE there because that's a very exciting mission coming up, right? Yeah, I'm assuming that what you're actually checking is whether these things can communicate with each other and what the downsides to that communication might be. Is that right?
Correct. I think a common mistake that people make is that they test an antenna standalone. Actually, you were hinting at that. Mm-hmm. And then when you install it on a spacecraft, actually the radiation properties of that antenna change. So you have to do testing of the full system at any point in time. So you really can create nulls, so basically no transmission in the direction to Earth if you're not careful. So we have to do that test.
Yeah, that would be pretty awful, wouldn't it, if you sent something off to Jupiter and it just so happened to be sitting in the shadow of its own spacecraft.
Now, I think the camera that we have here does not do justice to the room. I have to say it's huge inside here. Of course, you have to fit full satellites in it. But one of the questions I had, it also has a very particular shape, which I find it difficult to describe. Maybe you can, but I was wondering if the shape has something to do, or is this all about the blue cones that do the magic?
It's a combination, of course, of both. Like I already said a little bit in the beginning, we have to mimic space. So there are a couple of things that we have to do. And the reason, in the good old days, when I already said the previous name was compact payload test range, is that it is, according to our definition, it is compact, because what we're trying to mimic is a spacecraft hundreds of kilometers, thousands of kilometers in space, and we do that in tens of meters. Yeah. So I don't know if you can see the big white mirrors, Matt. Can you see the big white mirrors?
I can, yeah.
So just right on top of my head.
Yeah.
Julio's wearing them.
Those are very important. So we have a transmitter for the viewers, probably.
I think you
on the left.
Yes.
The viewers on the left. Yeah. So we transmit a signal, which is a sphere, and then the two mirrors, what they do, they actually shape the sphere into a plane wave. And the plane wave is important because that is what the satellite sees when it's hanging in space thousands of kilometers above the Earth. So that's one thing. So that is important for the shape of the room. And the second thing, if you're in space and your antenna doesn't collect the radiation, what actually does happen is that the radiation just goes into deep space and never comes back. So you don't get any reflections. And in that case, the cones are super important because they prevent any reflection going back. So the shape and the white large reflectors that you see make sure that in tens of meters we create a distance equivalent for the antenna as in deep space, and the cones make sure that we don't get any reflections back.
So it's just you're mimicking the distance that these things are away, because when you transmit, obviously you're transmitting in a kind of point source ball.
Yep. Yes.
But by the time it gets out to space, it looks like it's flat, straight waves. Okay. Yeah.
So if you're very far away from a sphere, the radius is so large that actually you don't see that it's a sphere anymore. You just see a very small piece of that sphere, and actually it looks like flat.
Yeah. I just about get it. But presumably that's I guess that's why when the sun's so far away, it casts very sharp shadows, right? And that's why you can tell that flat Earth people are completely bonkers. one of the reasons.
I'm not going to comment on that one. I'm going to use the analogy of the the waves in the ocean. So if you go to the beach, actually what you see is a plane wave coming towards you. And it has started somewhere, that wave. But the effect we see is just like a plane wave coming towards us.
Because the curvature it's so wide that you don't see it anymore.
Yeah.
Exactly. Yeah. By the way, are you aware of any other facilities like this one around the planet?
Yes, there are several. The more interesting bit to highlight is that ESA has a function of trying out new technologies. And this is a very good example where in the early days, and I'm talking back probably 30, 35 years ago, people didn't really believe that this was a method that was useful to measure antennas in space, so that it would never work really well. So we did bite the bullet, and we just built a much smaller one than this one, and we demonstrated that actually the technology worked really well. Then afterwards we built a larger one, and now I think industry is completely convinced that this is a very good way of measuring antennas, that every big industry, every big prime that is building satellites has a room like this.
You were talking about the history that you guys built a smaller one.
Yes.
When are we talking about? When did
That's
this
about 35, 40 years ago.
Okay.
Yeah.
Okay.
And this one is probably 20, 25 years old. And we're up for a new one because even though the dimensions are 25 meters by 15 by 10 meters, it is getting too small for the satellites that we're facing in the future.
So satellites are getting bigger and bigger.
They're getting
rockets
bigger
are getting bigger and bigger.
Yes. So we have to grow as well.
I even heard that there are some ideas to have fixed 7-meter diameter antennas.
That's already happening.
Yeah.
Actually, one of the missions that we selected, Simmer, has an even bigger antenna. So we're already there. It will still fit in this room. But in the future, we're probably going to go to 15, 20-meter antennas. So we really need to grow as well.
So the downside of people like Elon Musk and Jeff Bezos building massive fairings is the fact that you now have to have a bigger room to put your antennas in, right?
I think a drive is always. I don't think it's Elon Musk, but I think it's the imagination of scientists that never stops. Okay. I think it's the scientists always want more accurate measurements. The telecom as well. We want a very small mobile phone, but nobody's allowed to see the antenna, so the antenna doesn't have any gain on your mobile phone, which means that we have to build bigger and bigger antennas on the satellites that we launch.
Plus, so, I mean, as usual, when you see a rocket, I mean, many missions are limited by what you can fit inside the fairing. If you would let the mission designer, if you could tell the mission designer that you can teleport that into space, I'm pretty sure we would have much bigger spacecraft than what you can fit inside the rocket. So it's a limiting factor, I think. I mean, what size of antenna would you like to see in space? Imagine if we could have something like the Deep Space Network size antennas in space.
I think people are already considering 30, 35 meters for missions. So I don't think it is going to take too long before we're at those diameters. So, and then, I'm going to repeat the answer that I just gave to Matt. I mean, give it to a scientist, he wants 50 meters, he wants 100 meters, he's going to want 150 meters, he's going to wish an array of satellites carrying 150 meter antennas. So there is no end to, let's inventing the future.
Okay, let's speculate a little bit. If you could have those antennas on those sizes in space, what would be the use of that? Would it be to communicate with deep space probes, or would you do some sort of science as well? Could you?
I think the communication. I think at one point in time you want more data, so that translates into a bigger antenna, but that's probably going to flatten out. I think scientific use cases are the ones that will never stop. So the imagination of people is endless. So they want to have with higher resolution images of, for example, what Hubble already does. We want to improve on that. We want to go to a factor of 10 better, 100 better, 1,000 better. So science, I think, will always be the driver for crazy stuff in terms of very low frequencies, in terms of very high frequencies, in resolution. And you just name it, it's endless, really.
Yeah, because I guess the using antennas in space isn't just about communications. Presumably, you can do things like pass radio waves through objects and see what they look like inside, and all those kind of scientific things that I can barely scratch the surface of.
Yeah, and what I always find amazing is that a lot of people look at the same object in space. It could be a galaxy or whatever. But if you're using different frequencies, and different frequencies could be X-ray, could be UV, could be infrared, radio waves, the high radio waves, the low radio waves, you get different information from each of those measurements. So sometimes it's difficult to explain to people. We're going again to look at exactly the same thing, but at slightly different frequencies. And then they're like, yeah, but you already looked at it. But the science is completely different behind all of these measurements.
Yeah, I mean, I think the general public, on the whole, don't understand that we only see a sort of small chunk of the light spectrum, and I guess that it's like, well, if you can keep going up and you keep going down, there's either side, and you can use electronic eyes to see that light.
Yeah, correct. I mean, a good example is if it's foggy, actually you can't really see light very well, but radio waves can penetrate, so you clearly see the advantage of looking at different frequencies at exactly the same object.
Yeah, I mean, I suppose even your mobile phone is really looking at the light that's coming into it, right?
Yeah, you could say it like that, yeah.
Just a slightly different pair of eyes than we have.
Yeah. I mean, on that note, I think we need to... It's going to be a little bit hectic today because we will have to be moving from one interview to the next. So, Peter... thank you so much for
my pleasure.
Having to. I think it would be interesting to have him for a full podcast one of these days.
Yeah, that's the problem. We're used to doing like sort of hour and a half type ramble chats with our guest.
Yeah.
So I guess we need to get out of that mode.
Yes. But
I'm going to pass over.
Thank you, Peter, and we'll see you in the next time. So
thank you.
Now we are going to. We have another guest today, a surprise guest. We have a question from someone if this will be uploaded to our Spotify account later. Yes, Matt, I think the idea is that we will take these different interviews and we will put them in the main podcast, right?
Yep. Yeah. It'll be all coming out in various podcast episodes, available on all platforms, including Spotify and iTunes.
So look who we have here. A veteran of the podcast, let's say. He was already with you in episode 50, Franco Ongaro, wearing two hats, director of tech here at ESA, but he's also the head of site here at Estec. Welcome, Franco, to the Interplanetary podcast.
Thank you, Julio.
Welcome
good
back.
Good afternoon, everybody.
Welcome back, indeed. Actually, you were in the podcast before I even heard about this podcast.
Well,
surely you heard about it before then, Julio.
That's the only advantage of being old enough.
So, yes, camera is there. The public is watching us there. Okay. The microphone, and I would say we start with the next interview. Well, Franco, thank you for joining us here today. I assume you are having a busy day because this whole event happening here at ESA. This event, it's an ESA Open Day, and but yesterday we had an on-site day here in Estec, and one of the reasons why I wanted to ask you here for everyone is if you could tell us a little bit, as head of Estec, a little bit of the history of this site. How did it came to be this amazing campus that we have here?
All right, that's an interesting question. It takes us back to the very birth of the European Space Agency. This was basically the same two scientists who have started CERN, Amaldi and Auger, and they realized that as much as Europe needed a CERN for nuclear research, it needed a CERN for space. And that was the whole starting point of what at the time was the European Science Research Organization and European Launcher Development Organization, which merged in 1975 to become ESA. When you start such an organization, then you expect that there'll be centers to run it, like CERN is in Genève, and they started looking around for where to put what. The headquarters went to Paris. One scientific center went to Frascati near Rome, as in today. The operation center went to Germany, Darmstadt, ESOC. And of course, it was clear to everybody, back then there was no company able to build a satellite. So they had to build a factory for making the first European payload satellites. And they decided it had to go to a small country. And which small country were part of ESA at the time? Well, the Benelux and Norway. Of course, Switzerland as well. Now, Switzerland already had CERN. Euratom was in Brussels. So the Netherlands came forward with a very convincing offer to have their technical center built there. And this is how they decided first to put it in Delft. Then you have to realize that Delft is on a polder. And if you have to shake big spacecraft, you need very heavy machinery. And that heavy machinery would probably sink in the polder. Mm-hmm. So that's why we ended up here on the dunes between Noordwijk and Katwijk.
Oh, I find it counterintuitive that
No, because we have to keep up the test center where we are. We have steel poles that go down 25 meters in the sand and are keeping us very well stable. And the sand itself is immersed with respect to the polders. So it's a very stable substrate on which to build Estec. The building started in the early 60s and it ended around 65, 66, and the center was officially inaugurated by Princess Beatrix, who then became queen, and now is again princess. Quite
a career.
Yeah, and we were from there onwards. The site saw all of the missions of ASRO and ALDO being developed. Clearly, from the very start, if you look at the way Aztec is, you can do that on Google Earth or on our website, you recognize the making of a factory. There's a big, long, central corridor in which spacecrafts were to be assembled, and there are fingers perpendicular to it, which have the laboratory, and where the parts for making the satellites were built. And it all ended up here in the testing center, where the satellites were to be tested and then flown back. In time, of course, we fulfilled our mission to create an European industry. And today, European industry is second to none in terms of competence, quality, and capabilities. And in that way, we have transformed our own work. We are no longer building satellites here. We still test them before flying them because it is very convenient for the sector to have a place here where you can do testing for everybody in the sector. And rather than multiply these very expensive and, I would say, unique facilities. So we keep them, we maintain them, we make them available to all the sector, and they don't have to be paid multiple times. It also means, not even a shovel as a tool is very useful if you don't know how to use it. So it's not only the center itself, but it's the competence of the people in it that make all the difference. And this is a contribution to the sector itself. So what we do today is we interact with the communities and understand what they need from us, what they need from space. We work on the preliminary analysis of these requirements to see whether the mission is feasible, whether it's affordable, and what technologies we need to develop in order to make it fly. And once our member states agree with it, then we go ahead, contract with industry to develop that mission, manage the industrial work, and at the end, they all come back here. We shake them, test them, fire them, and see if they work. And then they go out and go to be launched and go to space.
In the next few months, we'll have a whole Ariane 6 upper stage in one of these testing rooms. Not in this one, I think. Yeah, I can't wait for those tests and to see it here.
Absolutely.
Yeah,
It's there. With obviously the theme of the Open Day is inventing the future. What's Aztec's kind of place in terms of technology development?
Well, basically, we have conventionally we say you develop technology looking at it two ways. One is what we call technology pull, which means our scientists come up and say, hey, we want to look deeper into the universe in order to see what dark matter is made of. Yeah. Or we want to catch waves, gravitational waves. That's LISA. Those are spacecrafts at millions of kilometers from each other, kept very precisely by laser in position, such that when a gravitational wave passes, this moves one of the satellites with respect to the other, and we can detect it. Now, the scientists imagined this mission before the technology to make it is there. So we work on that technology to provide them with that capability. So this is what we call mission pull. How are you going to do this? In a sense, we have here in front the example of James Webb. You can clearly see that it doesn't look like any other telescope we've flown before. Why? Because if you have to make a mirror that big, it won't fit into the fairing of the launcher.
Exactly.
So you have to make it such that it folds in space. And that is the technology we need to invent in order to be able to fly a mission like this.
You happen to have the folded version right next to it.
Yeah.
By the way.
Exactly. And by the way, there's Baby Colombo who's just passing in front of Mercury these days, so don't forget to go and watch the pictures. We saw him yesterday for the first time, and they're on our website. Now, Baby Colombo wouldn't have been possible without electric propulsion, because it would have just required too much fuel to do the mission with conventional chemical propulsion. So electrical propulsion is one example of the opposite, is what we call technology push. People started thinking that in space you can fire an engine for a very long time with a very low thrust and still gain velocity all the time because there's no resistance. And therefore, just by accelerating very rapidly ions out of an electrical engine, you could actually get to Mercury. And all of that with the power of the sun, without having to bring with you chemical energy. And this is an example of what we do, inventing technologies which do not exist yet, but they can enable a new thinking about missions that we couldn't do before. So how do we select? Well, we select on the basis of what's needed by the missions we have on the books, and we select on the basis of what technology is actually providing us with the best promise for future missions. What technology will make the missions smaller, cheaper, faster to build, and with the most return in terms of economies.
Yeah, NASA has the technology readiness level scale. Is that used by ESA as well? Is that or do you have your own system?
No. This is by now an ISO scale, so right. We use the same. If you're curious about our technology, if you go on our website, you will find a document which is the technology strategy of ESA. And it's quite interesting because we have what we call 10 competence domains is 10 groups, informal, of our experts who are looking across the different organizational units at what technologies we need for the future. And at the same time, in that document, you have the requirements from our mission. So you have the two together, the pull and push, and it gives you a very wide spectrum of what we're doing. And of course, we gave ourselves some very tough targets for the near future, as near as 2023 and 2030. By 2030, we want to reverse the contribution by Europe to the problem of debris in space, which means we don't want to create any more debris, and we want, if possible, and we're working on that mission, Adrios, to remove debris that's up there. We want to be 30% faster in getting our missions launched with respect to the time we take today. We want to be 30% faster in including new technologies in these missions, because one of the problems is we push for new technologies, but very often the mission managers tend to be very conservative. So you need to somehow force them to adopt new technology, which is always a risk, of course. And finally, we want to be one order of magnitude more cost efficient with every new generation of spacecraft. And this may sound very difficult to achieve, but if you compare a mission like Hipparcos, which measured 1 million stars, and a mission like Gaia, which measured 2 billion stars, so 3 orders of magnitude better, in actual equal cost, meaning factoring
the return on the cost.
Factoring inflation, they costed the same amount of money, but one had 3 orders of magnitude the performance. So that is what we can achieve from one generation to the other. So those are very ambitious goals that we've given ourselves for our technology to develop.
You mentioned something very interesting with the mission managers, because if I understand correctly, then some technologies we start developing them before even there's a mission for them.
Yes.
Because if you would study that mission development at that time, that mission would be very risky to engage in, right? But then you mentioned as well the mission managers maybe being a little bit, I would not say scared, but shy conservative about getting this new technology. Why is that? You mentioned risks.
Well, it's basically that, and this is an interesting question. It's a very good question, because our mission managers have a very tough job. They have to guarantee that the mission gets done and is successful. We have missions that cost anywhere from $500 million to $1.5 billion. And if you look at James Webb, then you're looking at a 15 billion mission. So it's a huge responsibility for a mission manager. And if he's known a certain technology and it worked well for past missions, and he's taking so many risks on new technology on his mission, then he's probably trying to minimize the additional risk to his own mission. And there's something which is very typical, which is flight. You can simulate a lot on ground, and that's what we do in this area. But the real proof is in the pudding, which means is to fly the technology and see how it behaves once it's in space, because that gets you through the full cycle. So one way we've found to shortcut this, let's say, barrier and to give more confidence to our mission managers is to have what we call IODs, in-orbit demonstrations. These are small missions which have very low risk in terms of cost and even exposure to the public if there's a failure. And they allow us to fly these technologies ahead of time very quickly and prove to the mission managers that these are technologies that do indeed work in space. They've been launched before. So we gain for them that confidence that allows them
to demonstrate that they work before using them on a critical mission, correct?
Precisely that, Julio.
Yeah.
I mean that's something I've spotted with kind of space missions is sometimes you've got this technology lag where you've got technology that's available on Earth that obviously takes some time to get out into space because you've got to kind of prove its space worthiness before you send it. So you've got solar panels that are much better on Earth than the ones in space because you're not sure that they'll work in space.
Yep. But
actually, I must admit the solar panels are a tricky example, meaning today the most performant solar cells are going to space. There are quintuple junction cells, and they're about 37% efficiency. The only problem is they're a little bit too expensive to put on the roof of your house. So that's why you don't see them yet going on the roof, but you will. I mean, frankly speaking, space was the world that took solar cells out of the lab and into practical use because we didn't have an alternative in space. No hydrocarbons to be used for energy in space, so we had to find another way. But where you're really right is if you take Julio's
my cheat sheet.
Yeah, your mobile phone, and you put it through the works here, and you also irradiate it with the kind of radiation it will get in orbit, it will not last very much. And in order to make sure that the electronics we put in space will perform reliably, we need to actually make it space-proof. And if you look at a world where new electronics, new generations come out every 6 months, and you think of the typical space mission time, which is about, depending on the complexity, anywhere between 3 and 10 years, then you can understand that the moment you take a decision on the technology, by the time you fly, you're like 3 or 4 or 5 generations behind what you can find on ground. But the difference is you can rely on that one not to fail on orbit. And it's not only failure per se, but it's also, for instance, the reliability of one digit or a 1 and plus, a plus changing into a minus or something like that. Something that you don't want to happen to your critical systems. Now, the interesting things on IOD missions, and we've seen it on GOMEX-4 and on FISAT, there are 2 CubeSats. They were the first 2 spacecraft to actually fly an NVIDIA card, which is a card made for use with artificial intelligence. And they had a very miniaturized hyperspectral sensor, and the artificial intelligence chip on it was able to distinguish pictures with a cloud cover from pictures without a cloud cover, thereby reducing very much the amount of data that we have to store on orbit or send down to ground. And of course, a CubeSat cannot have a huge antenna, so the data rate at which you can send down data is very reduced. But this is why? Because it was a 1-year duration mission. It was a very cheap mission. And so we could minimize the type of modification we needed to do to that chip before flying.
Yeah, that's really interesting. So, I mean, is that a trend that things are getting cheaper, and therefore you can get more bleeding edge technology up into space in terms of particularly things like CubeSats?
Absolutely yes. Absolutely yes. And it's miniaturization, and the IT world is coming to us as well. So if you look at the performance of the camera on the phone of Julio, to have that performance 10 years ago, you had to have a camera like this.
Which I also have.
Yeah. And that is how basically that allows us to really miniaturize. And of course, as you reduce the size of your spacecraft, then you also reduce the material cost of the spacecraft, but also as well the launch cost, which are a big factor into getting to space. So all of this reduce your exposure and your risk for that mission. So your mission manager can really take some risks, and it's important because it allows to demonstrate what capabilities we can then work on for the larger missions.
With miniaturization, is that making it less likely to fail from radiation and miniaturization seems to be like the smaller you get it, the more prone I would have thought it would be to radiation, or am I just wrong about that? Or is there no connection?
No, it's a very, very good question, and maybe really a question to the edge of my own competence, because I'm more of a system engineer than a radiation expert. But if I can make a visual picture for our public, if you take radiation as balls of different size and different speed, they will have different effect on your circuit. So going smaller and more concentrated will make it more prone to damage by some of those, but less prone to damage by some of the others. So it's a fine...
must be a sweet spot somewhere, right?
Yeah, exactly. And that's what we're trying to find, of course, but it's not easy. You can also look at the problem another way. If you are producing chips for space, you're producing a few thousand maximum. The companies that produce chips for mass market, they produce billions. So it is very costly for them to work on our niche. And this is a real effort to understand where we can introduce ways to reduce the impact of radiation on our system. And that can be partially hardware, but that can also be software tracking and software watchdog systems that make sure that if what we call a single event upset, a bit change in sign or something like that, can actually be spotted and corrected without necessarily intervening on the hardware.
You've been at Estec for a while now. Is there a sort of proudest day? Is there a day that you can really remember and go, oh man, that was the best day at work ever?
I'm a really lucky man. I've had many of those. You have to understand that there are about 3,000 people in Estec, and I would say all of them are way smarter than me. So that not a day goes by that I don't learn something from them. And we had so many proud moments where we could see things that would work on for years, ideas that had been challenged, had to survive, and finally got through and became the winning proposition for a specific mission that very difficult to single one out. I've been head of Aztec and director of technology engineering and quality for it'd be 11 years in January. So I'm really part of the furniture now. And still sometimes you get in the morning, you watch around, you look around at this wonderful place, this incredible place, and you think, am I really the guy who's in charge of this? How is it that I got so lucky? So no, it's really, and today we have the online open day, And it's a little bit of a pity because when you go online, our colleagues don't get the direct questions, the direct interaction with the people who are visiting. But on an open day of 9,000 people, you could see how much these people were taken in by the passion of my colleagues. And yesterday we had this special visit by a very VIP group of people with physical challenges. And we could get some of that back, of this looking in the eyes and their enthusiasm reflecting back on us and say, this is why we do it. This is what makes us proud.
Yeah.
So I probably didn't answer your question.
No.
That was my answer.
It is. I mean, I was just wondering, if you had to just single out one mission, if talking to your great grandkids or whatever, and you just singled out one mission where it's like, I had a part of that. Which would it be? or is that like picking a favorite child?
Matt, you're asking like which one is your favorite kid?
Exactly. That's like which one of these you will send to university. But in fact, I've had my hand in a number of missions. And maybe the proudest day is still to come next year when we launch ExoMars, because I've actually given the name to the mission. So, and I was the one doing the first studies for it. And so I'll be looking to it with a lot of attention and enthusiasm. I'm extremely happy that it finally gets to fly.
Yeah. That's a long time in the making as well. There must be
absolutely
a few disappointments on the way there.
Exactly.
We have one question more related to pollution. It's talking about the many ways in which us humans pollute the planet, and the question is more specific: how do or if space missions pollute? We already talked a little bit about the removal of space debris.
Yeah. Well, we have a program that we call Clean Space, which is not only looking at cleaning up space, but it's also looking at what we call the life cycle environmental impact of our mission. So how much do we pollute in producing them, in launching them into space, and then finally, not to pollute space, we have to re-enter them and dispose of them safely. We're working on it, and if I throw myself a little bit further, we're also looking at a circular economy in space, where rather than build to destroy, you actually build to recycle, like we're doing now on Earth with the cars, etc., and be able to recover that capability for future missions, because the big obstacle, the big energy expense is getting to orbit.
The launch itself.
Yes. After that, if you're up there, it's like free mass for you to use. The other thing we're doing is, of course, we're greening Estec. So we've been greening Aztec for the past 10 years, but whether it's by using green energy, whether it's by making sure that we can use the less energy to run the test center, whether it's coming by bus and moving the bus stop closer to Aztec or having a program for new bikes, well, we do everything to try and reduce our impact on the environment, because ESA is the larger provider of data on global warming in the world from space. We provide more than NASA and everybody else. So we are the first one to have the picture under our eyes and understand how fragile the Earth is. And Kate is on the space station, but we are all astronauts on spacecraft Earth, as Bob Hawkins used to say. And we got to take good care of our spacecraft because we don't have another one.
Franco, thank you for joining us today.
Thank you, Julio. Thank you all. Thanks for listening.
Thank you for this wonderful event. I was here at the event yesterday as well, and it was very inspiring. It was very good to see and have all these colleagues, volunteers coming together and and helping and working here and explaining to the public. And you get a lot of energy when you meet the public in person. I have to say it's one of the most motivating events that you can get here at ESA during the year.
Absolutely.
Thank you, Franco.
Thank you. Thank you very much.
Thanks very much.
Till next time.
Awesome.
The Interplanetary Podcast, putting the ace back into space.
That was Julio and myself at Estec earlier this month. If you want to know more about the podcast, go over to www.interplanetary.org.uk, or if you want to join me and all the Spodcats on Discord, etc., and get some t-shirts and mugs, etc., then why not go over to www.patreon.com/interplanetary. It's people like the Patreons that keep this podcast going. They are utter legends, and I can't thank them enough. So, until next time, bye-bye, Spodcats!